In the last video, we covered most of what PCA is all about. Now, let's see if there are any issues with using PCA to find the direction with the maximum variance to rank student performance. If we take a closer look at the coordinate system of the original dataset, we can see that 3 students excel in science, which means they have high science scores. Meanwhile, the other 2 students, although their science scores are relatively lower, clearly perform well in humanities. This is a common phenomenon in real life, so we can divide the students into 2 categories, representing them with 0 and 1 respectively. Please note that using 0 and 1 falls under label encoding. This approach is more suitable for ordinal data than for nominal data. Here, we're just using it as an example for analyzing PCA results, so we won't go into too much detail about the advantages and disadvantages of label encoding. Using PCA, we might end up ignoring the students who excel in humanities. It tends to focus on a single performance aspect, essentially ranking students based on that one area. However, if our goal is to classify students into 2 groups, one that excels in science and another that does well in humanities, the single piece of information provided by PCA isn't enough. Then we need to consider the question, what should we do if we want to make it easy to distinguish the 2 classes? If we want to make it easier to distinguish between these 2 classes of data points, we should do 2 things. First, we need to make sure that data points within the same class are as close together as possible, even overlapping if we can. Second, we need to ensure that data points from different classes are spaced far apart. As long as we can achieve these 2 objectives, the dataset will have a strong overall pattern, and the model can efficiently recognize these patterns. In more formal terms, we need to minimize within-class variance and maximize between-class variance. This is exactly what linear discriminant analysis LDA does. LDA reduces the dimensionality of the data by projecting it onto a lower dimensional space where the separation between classes is maximized. Since LDA uses class labels to guide this process, it's considered a supervised learning technique. Here, we've made a simple comparison between PCA and LDA. Take a moment to compare the differences between them. We've already covered this content before, so I'll skip this page for now. If you need to review it, feel free to pause. Now, let's go through LDA step by step to see how it minimizes within-class variance while maximizing between-class variance. Similarly, the first step is to normalize the dataset. Since there are various ways to normalize data, the final LDA results may differ depending on the normalization method used. Next, we move on to steps 2 and 3, where we'll calculate the mean vectors. So, let's first talk about what mean vectors are. A mean vector is essentially the average of all the feature values for the data points in a specific class. It represents the center of that class's distribution in our feature space. Later, these mean vectors help us measure how far apart the classes are, which is key for maximizing the separation between them. First, when working with a dataset, it's important that everyone understands what a mean value represents. We calculate it by taking the average of each feature's values. That's the essence of a mean value. If we combine the mean values of different features into a single set, we form a vector. That's the definition of a mean vector, representation of the center for those features. Based on the definition of a mean vector, we can calculate a mean vector for each class individually. Let's start with class 1. First, we extract all the data points from the dataset that belong to class 1, then compute the average value for each feature among these points. Unlike the average we calculated previously for all the data points, this time we're only calculating the average for data points within the same class. Similarly, by combining the average values of the different features, we obtain the mean vector for class 1. Similarly, we can extract all the data points in the original dataset that belong to class 0 and calculate the mean vector for class 0. Now that we've finished steps 2 and 3 of LDA, in the next 2 steps we need to calculate the within-class and between-class scatter matrices. So, let's start by discussing what a scatter matrix is. First, we have within-class scatters. This is the formula for the within-class scatter matrix. You can see that it has 2 main components. One is a measure of the distance between each data point in a class and the mean vector for that class. This is similar to calculating the variance for each class. Then, we add up the variance from each class to get a resulting matrix, which we call the scatter matrix. This matrix measures how scattered the samples within the same class are. The goal is to minimize this scatter so that samples within the same class are tightly grouped together. On the other hand, we need to calculate the squared distance from each class's mean vector to the overall mean vector of the dataset. Then, we scale that squared distance by the number of data points in each class. Finally, we sum these up to form a matrix that represents the between-class scatter. This matrix measures how separated the class means are, and our goal is to maximize it to push different classes further apart. Again, because calculating the scatter matrix can be quite complicated, we won't require you to compute it manually in this lesson. However, it's important that you understand what these matrices represent and what our goals are. For the actual calculations, you can rely on code to handle the heavy lifting. Now we have to scatter matrices. The goal is to minimize the within-class scatter so that samples within the same class are tightly grouped. To achieve that, we take the inverse of the within-class scatter matrix. The other goal is to maximize the between-class scatter, which pushes different classes further apart, so we use the original between-class scatter matrix as is. From this point, the idea behind LDA becomes similar to PCA. We want to perform dimensionality reduction while preserving as much of the original information as possible. To do that, we compute the corresponding eigenvectors, and the directions represented by these eigenvectors are the ones where the projection is maximized. Like PCA, LDA can produce multiple eigenvectors and eigenvalues, but we always select the largest ones. The difference here is that these eigenvalues don't represent variance anymore. They represent how well the data points can be separated. That wraps up our discussion on LDA. In the next video, we'll start talking about data discretization in data preprocessing.